Hello and welcome. Today, we are lacing up our running shoes because we are going to try and win the boot time race. We're diving deep into the QNX real-time operating system to figure out how to shave those critical milliseconds off your system's startup time.
So, you might be thinking, it's just a few seconds, what's the big deal? But you know, in the world of embedded systems, every single millisecond is precious. I mean, just imagine waiting for your car's digital dashboard to finally boot up before you can see your speed, or maybe a critical medical device that's taking way too long to become operational. In these scenarios, a fast boot time, well, it isn't a luxury. It's an absolute requirement for safety, for usability, and for a great user experience.
You know, the best way to visualize this whole optimization challenge is to think of it like a relay race. The process isn't just one single monolithic task. No, it's a series of stages, and each one hands off the baton to the next. So our goal is really twofold. First, make each runner in the race faster, and second, make sure that every single handoff is as smooth and as quick as possible. If you get both of those right, you'll be crossing the finish line in record time.
Okay, so here's our game plan. We'll start with the first leg of the race, loading the OS itself. Then we'll move to the second leg, which is where your own applications start running. After that, we'll learn how to check our stopwatch, to see if we're actually getting any faster. And definitely stick around for a bonus lap on optimizing systems that have graphical screens.
All right, let's get right into that crucial first leg of the race, loading the OS. This is often where the biggest gains can be made, mainly because it involves the fundamental task of getting the kernel and all the core services off of storage and into active memory.
At the heart of this first leg is something called the image file system, or IFS for short. The easiest way to think of the IFS is like a tightly packed suitcase. It holds absolutely everything the system needs to get started: the kernel, your essential drivers, and all of the initial applications. And it makes sense, right? The bigger and heavier that suitcase is, the longer it takes to carry it from flash storage into RAM.
So, how do we lighten the load? Well, there are three main strategies we can use. First, shrink your startup programs down to their absolute essentials. Second, strip out any and all debug printing or verbose logs from your release build. They just add unnecessary weight. And third, and this one is a big one, use smart compression strategies to shrink the overall size of that IFS suitcase.
So, the crucial point is this. A smaller IFS means less data to copy from flash to RAM. It really is that simple. Every single byte you manage to remove is a tiny bit of time saved during that initial critical copy operation. And trust me, it all adds up.
Now, let's talk about the trade-off you get with compression. QNX gives you this really powerful deflate utility that does a fantastic job of shrinking files. But, as they say, there's no free lunch. When the system needs a compressed file, the inflator resource manager has to spend precious CPU cycles to decompress it on the fly. So what you're doing is trading storage space for CPU time. The real key here is to find the right balance for your specific system.
And the baton has been passed. The OS is loaded, and we are now into the second leg of our relay race, launching the application stack. This is where your own code starts to run, and believe me, it's another prime area for optimization.
So let's look at a really common mistake. Here, we've got processes starting in what seems like a totally random order. Process B needs process D, but oops, D hasn't started yet, so B just waits. Then process C starts, and it needs B, which, you guessed it, is still waiting. You've basically created an unintentional traffic jam, where processes are just sitting idle, waiting on each other.
And here's the solution. By actually analyzing your dependencies and just reordering the startup script, you can eliminate those bottlenecks completely. See? We've launched process D right after A. Now when B starts, its dependency is already met, and it can run immediately. C follows, and boom, the whole system comes online much faster. It's all about understanding that chain of command. Now, a key tool for managing these dependencies is the wait for utility. It does exactly what its name says. It pauses the boot script and waits for something to appear, maybe a driver or a service. It's incredibly useful, but it can also be pretty dangerous. If you place a wait for too early or for too long, it can bring your entire boot sequence to a screeching halt. So, use it wisely and only when it's absolutely necessary. Okay, we've tuned the first two legs of our race, but how do we know if we're actually any faster? Well, that brings us to the most critical part of any optimization effort, measurement. Because you simply can't improve what you don't measure. This is the question you have to ask yourself after every single change you make. It feels like removing that debug code made it faster, but did it? Really? Did reordering those processes actually help?
Without hard data, you're just guessing.
The answer is to use timestamps. By recording a high-precision timestamp at the beginning and the end of each critical stage in your boot process, you can get concrete, numerical data on exactly where your time is being spent, and more importantly, whether your changes are having a positive impact.
So how do we get these timestamps? Well, the QNX kernel provides a fantastic tool for this called clock cycles. This is a direct, super low-level call that reads the processor's own internal cycle counter. It's literally the most precise stopwatch you have available, and it's perfect for measuring those tiny intervals between boot events with very little overhead.
Now, clock cycles gives you a really big, raw number. To make that useful, you need to convert it into human-readable time. The system page, which is a special data structure in memory, contains a value called cycles per sec. All you have to do is divide your cycle count by this value, and you get your result in seconds. Now you have hard data to drive your decisions.
All right, for our final lap, let's talk about something that's incredibly important in a lot of modern systems. Getting that first image up on the screen as fast as humanly possible, whether that's a simple splash screen or a full-blown user interface. So here are some quick tips for faster screen startup. First, keep your screen graphics configuration as lean as you can. Second, use a minimalist build file just for getting that first screen up. Third, make sure your splash screen app is super simple and efficient. Fourth, and this is a big one, use statically linked libraries. Yeah, the trade-off is a slightly larger executable, but it avoids the time-consuming process of the dynamic linker having to search for and load libraries at runtime. And finally, for more advanced scenarios, you can use a tiny primary IFS just for the splash screen and then load the rest of the system from a secondary one. So let's just quickly recap our whole race strategy. For the OS load, the goal is simple: shrink your IFS. For the app stack, analyze your dependencies and create the most efficient startup order you can. And for everything you do, and I mean everything, measure, measure, measure. Use timestamps and clock cycles to prove that your optimizations are actually working.
And that brings us to the finish line for today. You've followed the guide, you've shaved seconds off your boot time, and your system is faster than ever. But remember, optimization is a continuous process. So the final question I want to leave you with is this. Now that you've solved this problem, what's your system's next bottleneck? Happy optimizing.